Okay, hello everyone. Thank you for joining our monthly webinar organized by IEEE's Instrumentation Futures Technologies Committee. Today's speaker is James Garrison from Purdue University. He will be speaking to us about the current progress being made in advancing signals of opportunity, which is an emerging field in microwave remote sensing that uses existing anthropogenic signals, think of communications and navigation satellites, as sources for bistatic radar. His work in signals of opportunity has required the development of novel instruments, signal processing techniques, geophysical modeling, and data assimilation methods for remote sensing, which he will discuss today. James Garrison is a professor in the School of Aeronautics and Astronautics at Purdue University with a courtesy appointment in the School of Electrical and Computer Engineering, where he was elected as a university faculty scholar in 2022. He is also an IEEE fellow and is the principal investigator for SNOOPI, a NASA mission to demonstrate remote sensing with P-band signals of opportunity. We ask that you wait until the end of the presentation for the Q&A session, so we will hold questions until the end, but please feel free to put your questions in the chat or Q&A box. And with that, we look forward to his talk. Please take it away, Professor Garrison.
Yeah, sorry, my name is Jim Garrison. I'm giving the monthly webinar on the science and technology of signals and opportunity remote sensing. Start off with, I'll give a short outline or introduction to microwave remote sensing, short history of signals of opportunity, which we are used the acronym SoOp, S-O-O-P, and talk about the history, beginning with GNSS reflectometry, then moving into more recent work on different frequencies, both in the instrument development, algorithm development, and the experiments and science development to support those. And I'll talk about some conclusions and future directions. Okay, this is GRSS, so I'm only going to spend a minute saying what remote sensing is. I'm sure most people in the group know what it is, but basically, if we're wanting to use electromagnetic radiation to make a measurement about something on the Earth, we're limited to two windows: the microwave window, shown over here to the left, and the optical window to the right. So these are the same windows which radio astronomy uses, and because Earth's atmosphere is somewhat transparent at those frequencies, it's largely opaque to all of the other bands. Okay, so we're talking about the microwave window here, about maybe 3 decades of frequencies from approximately 100 to 300 megahertz up to about 100 gigahertz. So the classical approaches to microwave remote sensing are either passive, using the emission from surfaces or the atmosphere, and then extracting a brightness temperature, and from the brightness temperature, estimating this emissivity, and this emissivity can be related to a number of geophysical parameters. A classical application is soil moisture, where we show that the emissivity is related to volumetric soil moisture. The other approach is active radar, or also called scatterometry, in which we use a radar pulse transmitted to the surface. We look at the returned signal power, and we can extract a scattering cross-section. And classical application of that is ocean surface winds, where here we show the scattering cross-section for a given wind speed as a function of wind direction. And through multiple look angles, you can independently estimate the direction and the speed. Okay, signals of opportunity builds upon this idea, where instead of using our own transmitter, we use an existing transmitter, but so in a sense it's passive, but we are using a human-generated source, so it is also active. So we have a non-cooperative transmitter. That's also an important part of this. We are using existing signals as opposed to transmitting our own signal. We have an incident signal, and we have a very small backscattered signal, and this is what most active radars would use. And I indicated this symbolically as this very small pattern here, the backscattered signal. But we have a much stronger forward scattered signal, and we also have the direct signal for reference, and these are received by a passive receiver, and by doing some type of signal processing, by comparing the reflected signal, the forward scattered signal, to the direct signal, we can estimate properties of the scattering surface. All right, and I like to say that SoOp is the third way of microwave remote sensing. We also see the term reflectometry, which was maybe the first term that was used when we were talking just about GNSS. So the typical observables we can get from the electromagnetic signal from the forward scattered signal will be reflectivity at the surface, a phase. We can look at how coherent the signal is, and we can also generate this delayed Doppler map, which gives a bit more detail in the paths taken by the scattered signal. And from these, models have been developed to invert these observables and extract geophysical retrievals of ocean winds, altimetry, soil moisture, wetlands, sea ice, above ground biomass, a number of different geophysical retrievals. Okay, so let's talk about the history of signals of opportunity. This is actually not a new idea. Signals of opportunity goes back to the earliest days of planetary exploration, in which it was found that information could be extracted from communication links from interplanetary probes and extract information about the planetary atmosphere, which led to radio occultation, which may be sort of in the signals of opportunity space. But also reflected signals can be used to make various measurements of the planetary surface. So I just show this example here from a scattering of a communication link from a lunar explorer mission in the 1960s. And they were able to make measurements about the something about the structure of the lunar surface, which became important for the later moon landings. For Earth applications, this paper from the 1970s was a demonstration using a communication satellite and an airborne receiver. And they were able to show sort of what we later show with GNSS reflectometry using the Doppler spectrum of the reflected signal. There was also, so these ideas all, pretty much used, different types of communications links. So going to GNSS in more recent times and starting in the 80s, this is the earliest paper mentioning the potential use of GNSS signals for scatterometry, for ocean winds. And the interesting thing is that the conclusion of this paper was it was incapable of giving useful performance, but that was because they were looking at backscatter. Okay. And then the paper which got me into all of this was from a navigation project that was published in the Institute of Navigation in 1994, in which they were looking at these flight testing of this fighter jet that had a GPS receiver on it. And they would notice it would occasionally lock onto the signal reflected from the ocean surface. And this was a problem for navigation. So they did a quite extensive study looking at what the reflected signal looks like and why it's capable of being tracked by the receiver as if it was a direct signal. And that's kind of what led me into all of this stuff. There's also this other paper that's also cited quite frequently for the first use of a communications satellite source, but I think the other one I found was an earlier date. But the important thing is this led us to look at navigation signals and the unique properties of navigation signals and why they're able to be processed when they're reflected from the ocean surface and treated in some ways like actual navigation signals. Okay, so as I like to say, the history of SoOp, I call the previous two slides a prehistory, and I'll say history begins when we define the concept that basically we're going with now for GNSS reflectometry. And there's two threads that happened independently in this area. The first one was in STEC, in the European Space Agency. Manuel Martinera published this theoretical study of a use of GNSS reflectometry for altimetry. And he came up with most of the basic principles that we use today. He looked at the delayed Doppler mapping, the tracking altimeter waveform. And then independently of that, right when I was finishing up my thesis on a navigation problem, I was collaborating with another engineer at NASA where I worked at the time, Stephen Katzberg, who was looking at altimetry. The TOPEX was going through its development at that stage as one of the first ocean altimeter. And we looked at altimeter waveforms, and then we came to the conclusion that the cross correlation used in GPS signals for tracking and estimating the delay is essentially the same signal processing as the match filtering used in an altimeter waveform. So many of the properties of an altimeter waveform could be used in a similar way, looking at reflected GPS signals. And again, these were independent at this time. Except we weren't really interested in altimetry. We looked at the idea of measuring the surface roughness, was also, byproduct of altimetry, and translate that into the wind speed. So we built a prototype receiver. I have this on the next page. That is me in 1996. This is our prototype receiver that we built using a development kit for a specific GPS chipset that was being sold at that time. This was still in the early days of commercial GPS applications, so there was some competition to develop new chipsets, and this one company sold a development kit that we could reprogram for this purpose. And we were able to collect data, and the previous plot shows our first demonstration that there actually is an effect of spreading of this correlation function. This now shows where I actually did my first retrieval and compared it with the Topex wind speeds, and we get some type of scatter plot that indicates it's feasible, and we generate some statistics from that. Okay, so let's talk a little bit about where GNSS reflectometry went. I should also say, interchangeably, and maybe not very precisely, interchanging the terms GPS, Global Positioning System, which is the name of the system operated by the United States, with GNSS, Global Navigation Satellite System, which is a generic term for any of the current 4 systems operated by national agencies. So I'll use those terms interchangeably unless I need to specifically talk about one system. Okay, so let's talk about the basic properties. Now, navigation signals are designed to measure a time delay. That's the basis of navigation. So let's look at a flat Earth problem, maybe an airborne receiver, tower-based receiver, a satellite out at infinity. I have parallel rays reaching the surface, and from a basic physics of a mirror reflection, we have a virtual point below the surface, and we have a specular reflection to the receiver. So this is essentially the same problem as if I moved the receiver below the surface and just carried this ray path down, conceptually down below the surface. So I would expect the receiver will treat this just as it was in the other navigation signal and estimate a delay. And it does it by cross-correlating the received signal with the model and tracking this point. Exactly same as done for navigation signals. This is essentially what the paper from that French agency that was doing that fighter jet flight test observed. They were able to track the signal as any other navigation signal, leading to erroneous positioning results. Okay, so now to look at the surface gets rougher, some interesting things happen. One is that I get multiple ray paths reaching the receiver at different delays. So now when I cross-correlate with my model signal, I don't get a single peak, but I get a superposition of the cross-correlations from all these different delays. And since the delays are always longer than the specular point, I get an asymmetric cross-correlation. So I get this long trailing edge. Okay, so as the surface gets even rougher, I get a wider distribution of delays. My waveform spreads out more. Right? And this basic principle, it can be observed in optical light, from just observing the sunset. It's one image shows a specular reflection where I have the sun visible here, and I have sort of an image of the sun. Now, if I do a rough surface, this is the classic picture that's been shown at all of these conferences. It was collected, at the first conference, which happened to take place in Spain at the time, but this picture was taken in France. Where we see that we don't see an image of the sun, but we see a spread of the reflected power over some area. And as we look at this rough ocean surface here, we see a wider spread versus here where the surface is smoother, we see a smaller range of delays. All right. So if we look at this problem further and we start mapping points on the surface to the delay in the signal, and also look at the dimension of Doppler, because during the time we're making these measurements, the receiver is moving, the transmitter is moving. So we get this Doppler effect too, and it's maybe not as easy to visualize, but we get the spread in Doppler as well. which actually that first example I showed of the communication satellite measurement actually looked at only the spread in Doppler. All right, so if we have a scattering surface, we can plot lines of constant delay as ellipses approximately on a flat surface, and the lines of constant Doppler as hyperbola. Even though this is such a big hyperbola, it look like straight lines, but if I looked at the bigger picture, there'd be hyperbola. And if you look carefully, you see that for most points on the surface, there are going to be 2 points that have the same delay and the same Doppler. They fall within the same ellipse, and they fall within the same band of Doppler frequencies. So these are going to be mapped to, when I calculate my plot of delay of my cross correlation versus delay and Doppler, my delay Doppler map, I'm going to see that those are both mapped to a single point. So the scattering power of both of these 2 points that are spread apart on the surface map to 1 point in the DDM, except for this one line between A, O, and B, which is mapped, which I can see is a single intersection between the delay ellipses and the Doppler hyperbolas. That maps to A prime, O prime, B prime, which is the ambiguity-free line. Basically, some of the basic principles of the delay Doppler map, the ambiguity. Okay, so now the other thing I want to talk about with the delay Doppler, I showed that example with the sunset, and we talked about the coherent, which is a single path delay because this path is smooth, so I can form an image of the source, or the incoherent, where I have scattering over a diffuse area where the phases all add together, whether the phases don't add together, just the power adds together. And so if I look at what the DDM looks like, and these are both plotted on the same scale, so you see that for a coherent reflection, I get, again, everything around the single delay. This would be, if taking a slice through this curve in this direction, I will get my example I showed previously with the cross correlation. I'm not including Doppler in this direction. But now if I include Doppler and I look at what happens with the incoherent, I get this horseshoe shape like I showed before. Lower power overall, but spread over more delay and Dopplers. Okay, so if we look at the mathematics to represent this, this is a model for the delay Doppler map. It is a radar equation where I have some input EIRP, transmit power, gain of the transmitter. Okay, and then instead of a point scatter, it's scattering all over a surface. So I have a normalized bistatic radar cross section as a function of my position on the surface. Now the surface is random, so the delay Doppler map at a given time is going to be a random variable. So these angle brackets indicate the expected value, and it involves the so model for the expected value, the mean value of the delay and Doppler. In units of power or energy, because I've squared it. And I have a normalized bistatic radar cross section over the surface that quantifies the amount of scattered power versus incident power. It can vary over the surface. It's a function of this position vector that defines mapping on the surface. It could also depend on the measurement, the roughness, the polarization, all of that. The ambiguity function describes this cross-correlation process, which has the effect of mapping out the areas in delay and Doppler. And then all of this stuff is just the geometry of your basic radar equation. So I have the 1 over r squared loss, the effective area of the isotropic antenna, and all of that. I included the receiving antenna gain inside the integral because I could have a gain pattern projected onto the surface. Okay, we also use the term glistening zone to indicate the area of the surface that is illuminated by the source. Okay, so some examples, I don't want to go through too much of the math right now, is the specular reflection. Again, I have a single path delay. So if I write my scattering cross section, I'm going to have a Dirac delta function here, indicating I only have power in the specular direction. And I can express my scattering cross section in terms of this reflectivity, which is the magnitude square of the Fresnel coefficient. Fresnel coefficients, well known for different polarizations. We use circular polarization because the sources are circularly polarized. And the dielectric constant, which shows up inside these reflectivities, depends on, again, the material properties. So in the case of land, it will be things like soil moisture, case of the water, it'll be sea surface temperature and salinity. Okay, rough surface, things get a little more interesting. This is the model for a scattering cross-section of a rough surface. And I'll just quickly talk about the different parts of this. I have my Fresnel coefficient here, which talks about the material properties on the surface. I have this vector Q, which if I look carefully at Q, I see I have my transmitter at the A point on the surface. Let's say the specular point's at the origin. And this point on the surface is defined by a two-dimensional position vector, which would be rho in the previous plot. I probably should have cleaned up my nomenclature a little bit. And some random variable zeta, which gives the height above that surface. So I have like a plane and I have my random surface on top of that plane. Okay, in transmitter to some point on surface to receiver, this Q vector is the bisector of these two vectors, the incident vector and the reflected vector. Okay, so this is a probability density function in terms of this vector Q. And let's talk about what that means. That is actually gives the slope of this Q vector. And if I think about what that means, if I look at a little facet on the surface and I have my Q vector aligned with the normal to the surface, so this would be then this would then be what would this be? This would then be then aligned with the normal to the surface. So basically what this probability density function is telling me is the probability of having a facet with this orientation on the surface. If they're not aligned, then this is giving me, the probability that I'm not aligned. And if it's not aligned, then my specular reflection with this little facet is going to be scattered off in a direction that doesn't reach the antenna. So this kind of gives a conceptual interpretation. This is a classic result from this paper by Barrick back in the 1960s. Okay, so skip over a bunch of work that I was involved in, many others were involved in with GNSS-R. It ultimately culminated in the Cygnus mission. This is video from University of Michigan. This is early results of the scatter plot. There's improved results since then. But basically, this turned this concept from these airborne experiments and some theory to a NASA satellite mission, an 8-satellite constellation, which gives coverage in the tropics, and you can kind of see from this early simulation how the coverage is built up by these multiple specular points. Okay, so now I want to pause and ask the question: why navigation signals? Why GNSS were used for this application? The first reason I'll say is that because they're designed to be range coded, they're designed for measuring a delay and Doppler, because that's the basis of navigation, versus communication signals, which are designed for transferring bits between one point and another. Okay, the data that's overlaid, the modulation on navigation signals is referred to as chips, because they don't transmit any data. For the system to work, I need an identical copy of the modulation that's on the signal inside the receiver. That's called a pseudo-random noise code, or PRN code. They also occupy protected spectrum, so they have some protection from interference or things like that. L-band is kind of middle of the electromagnetic spectrum for microwaves, and kind of towards the lower end of microwaves. And it's good for soil moisture and salinity. SMAP, SBOS, those missions all used L-band, and has some complications with ocean winds because there is structure on the ocean surface which is smaller than L-band, so we need to correct if you're going back to like a wave spectrum model or a mean square slope model, there's correction that need to be made to get those to agree with the measurements. More importantly, I did not begin my career in remote sensing. I began in navigation, so I came into this with from a background in navigation. So that's my own trajectory through this. Okay, so what if we look at other signals? Well, there's approximately one geostationary satellite slot per degree in geostationary orbit. So there's a little more than that. So there's about 450 transmitting satellites in GEO. Being a source in geostationary orbit has some advantages. One is that the incidence angle on the surface of the Earth is pretty much constant. Satellites may have a small inclination that gives them some variation in incidence angle, But that could be useful for calibration, removing the effects of incidence angle on navigation signals. I'm sorry, on reflected communication signals. They also have allocations in multiple bands, all the way from the bottom of the electromagnetic spectrum with microwaves, which would be P-band or UHF, VHF, all the way up to KUK band. I'll even go higher to like V-band, which we're looking at now for some of these high rate communications. But the thing is, they're not designed for ranging, they're designed for data transmission. But our hypothesis has always been that as long as the signals use efficient compression and encryption, they turn whatever communications signal they're transmitting into band limited noise. And that basically, if we can use the direct signal in some way as a reference, cross-correlating the direct and the reflected signal basically provides the same sort of delayed Doppler mapping as we saw with navigation signals. Okay, so we did some early experiments on this. I'll skip over those. I'll also say, why is this important to look at this is because the electromagnetic spectrum and microwaves is, I call it very valuable real estate. There's licenses for every one of these bands because there's a finite number of frequencies, finite range of frequencies that are within the microwave window, and there's a lot of competition for communication links to and from space. So as I've shown in yellow here, these are all of the bands that are allocated for space to Earth in communications and navigation. Okay, so with that in mind, our first application that I looked at using non-GNSS signals of opportunity addressed this problem of what bands could we use that would be useful for science, but there's currently difficult to make a scientific measurement in those bands because of allocation or interference or something like that. And then can we find communication links within that band? So it turns out P-band is very useful, and it fills an important gap in microwave remote sensing because penetration depth depends on frequency, roughly proportional to the wavelength. So this is a very simple two-layer model of the dielectric constant for soil. And I look at kind of two soil moisture values at these two levels, and I plot the penetration depth in centimeters for different frequencies, okay? And these two blue bands are GNSS. So this will be L-band, SMAP will fall somewhere in here. And we can see that's a few centimeters. We usually say like 5 centimeters for a high soil moisture. But if we go down to P-band, we see we can get down to maybe 20 to 30 centimeters. And that gets us a little further into the all-important root zone, which is generally about 1 meter below the surface. And so that maps the soil moisture that will be absorbed by plant roots, which is important for the understanding the hydrologic cycle. Any root zone soil moisture products that come out of SMAP or L-band measurements all involve some type of data assimilation. All right, so why don't we use P-band for remote sensing in conventional ways? Well, there's basically 3 reasons. One is the required antenna size to meet some diffraction limited resolution. So the size of this resolution cell is proportional wavelength over the diameter of the antenna. So as I go to longer and longer wavelengths, the antenna gets bigger. There was a design study in the mid 2000s called MOSE that looked at a soil moisture remote sensing instrument, and I think it was also biomass and soil moisture operating on 435 and 137 megahertz, and that required a 30-meter deployable mesh antenna. So this would be a very expensive mission, very complex technical mission to put together. And again, that was just a feasibility study. The European Space Agency is planning to launch a biomass mission, I think next year. It's also going to operate 437 megahertz with a 12-meter deployable antenna. And that, again, is a big mission, very expensive, long development time, complex technology. And biomass also has a spectrum allocation problem in that it's prohibited from operating within this region. The areas that's going to collect data are these red and yellow areas, and that's because of potential interference with space tracking radar. Okay, so the last plot here I show another effect of the RFI. And this is from a radio astronomy site, NRAO. And this shows the spectrum in P band from about 225 to about 480 megahertz. And I call out these two areas with this really powerful spectrum here. These are geostationary communication satellites. So our idea was, when we first started looking at P band, was, can we use these signals for remote sensing? Okay, so we wrote a proposal. We got funded on the NASA Instrument Incubator to build this airborne demo. This is on the NASA Langley aircraft. We have these side-looking antennas that use two elements, and we used a kind of primitive null steering to track the reflected signal. And we developed a prototype instrument to do this. We flew east-west, so the scattered signal is always in the direction of a geostationary transmitter, always somewhat to the due south over this instrumented area. And we only really process this data as a feasibility study. I mean, the data is still, I think there's still information we can get out of the data, but the main things we looked at were the feasibility of making this measurement. And some of the things we can see is we have this reflections over water bodies, so we get a strong reflection, and we also plotted the size of the Fresnel zone, so this kind of meets our criteria for looking at the resolution of one Fresnel zone. And also, I think this shows a river. We got a few examples of RFI at this one frequency, so we switched to another frequency for the remainder of the experiment. Okay, so based on that demonstration, we proposed SNOOPI, which was a NASA INVEST proposal for in-space validation of Earth systems technology. And in writing the proposal to SNOOPI, one of the things we thought very carefully about was, why do we need to go to an in-space demonstration? Why is this a time to do an in-space demonstration, and why do we need to go do an in-space demonstration? So we outlined 3 goals for SNOOPI that require in-space validation. One is to really validate this link budget, particularly the effect of coherence on these signals for an orbiting receiver at these long wavelengths, because our assumption was it's going to be coherent over more of the world than say L-band would be. We're going to also quantify the RFI effects, because our measurements previously have been airborne and in a limited area and somewhat remote area. But when we're in space, we have a small antenna with a very broad beam, so we may be seeing all kinds of sources on the surface of the Earth. And lastly, as a space qualification of the instrument, as kind of an engineering demonstration, we wanted to verify the instrument works, but also that it works with the required process for detecting and tracking these non-cooperative sources, because we are using sources that we don't have any control over. And so there is some uncertainty in their locations, their powers, and all that. So we have a approach in the operations to handle that. Okay, so this shows what SNOOPI looks like. It's a 2 by 3U with 6 U CubeSat. We have 2 antennas, and these 4 elements form an antenna on each side. One for the low frequency of the 255 megahertz, and then one for the 370 megahertz, circularly polarized, a single antenna. So we generate our delayed Doppler mapping through autocorrelation. This just shows a snapshot of the architecture for operating the system. And I said that was part of what we were trying to develop under this, where we need some elements, some 2-line elements for the orbit position of the sources. We need to propagate that forward to plan the data collections, and also adjust the range in delay and Doppler search, and then to conduct the experiment. So related to this, we came up with a mission planning tool that accounts for the kind of the unique geometry of depending on this non-cooperative source. So we can plan a region to make measurements in, or we can look at a typical measurement path and some mean value of what the climatology of what the soil moisture will look like, so we can determine if this is a useful experiment to conduct. And meanwhile, we are tracking memory usage on board the instrument. Okay, we also wanted to be able to monitor the source to get an idea of statistics on the power fluctuations, as well as the polarization of the transmitted source, because again, these are communication satellites. They are not designed for remote sensing. They meet some requirement of a polarization ratio in order to close their communication link budget, but they're not monitoring power or polarization to any level of accuracy that we need. And that data is not publicly available anyway, even if they did. So we designed this radiometer basically that can make radiometrically calibrated measurements of the source. This box is a thermally controlled radiometer front end that my students and I designed, having no initial experience with that sort of thing at the beginning. So this was a very good learning experience. And we also have this other antenna that's, I don't think it's visible here, but it's way in the background. So we can look at a kind of an array processing to estimate and time an angle of arrival that we can use to validate the orbit model as well. Okay, so these are some simulations on the retrievals. And basically, I looked at a range of reflectivities, a range of antenna gains of the receiver. Notice these are all pretty low antenna gains, and then the expected SNR of the reflected signal, and also the error in reflectivity. We also have a model for error in phase. We developed an end-to-end simulator for the measurement, and on the left-hand side, we have the end-to-end simulator, and on the right-hand side, this shows some preliminary measurements we made with our EIRP monitoring system that I showed earlier. Okay, we had an opportunity before the launch of SNOOPI to collect some test data. That was from this communication satellite that was using a type of software-defined radio that they were able to reprogram and capture segments of the data. In the end, we only got about a little less than 10 seconds. I used to have the exact number. I think it's 9.75 seconds of data. But we were able to show pretty much what we suspected was in the signal and confirm the order of magnitude of these signals. So if I look at the left-hand side, this is the autocorrelation center at about 0. And the right side, this is the autocorrelation center about the reflected delay time. So this actually should be a 0 here. Okay, so if we look at this, we see a nice strong signal in the direct. We still see a coherent reflected signal in the reflected signal. So we can track this this peak. Now, a couple of things we're going to see. One is the signal gets strong for a minute, and then also there's possibly an RFI event. I might have just missed it. It all goes really bright there. That may have been an RFI event. We saw where we got really high power across all the delays. Okay. So when we plotted this reflectivity, and again, we made a lot of assumptions about the geometry and about the calibration of the receiver, because none of these things were designed for this purpose. But relative change in the reflectivity, we mapped the points onto a Google map, and we see we get higher reflectivity over this lake, which was frozen at the time. And so, also this shows our time, and we show this peak in the reflectivity coefficient. We didn't know the antenna gain because we didn't know the attitude of the spacecraft. It was towards the end of its life, so it did not have very good attitude control. But we looked at a range of G over T's, and we could see this peak that corresponded to this crossing of the lake. So that gave us some confidence we did see what we thought we were going to see. Okay, this just shows some images of the integration and testing of SNOOPI. It was in a receiver in a deployer from NanoRacks with the BurstCube mission. This shows the Goddard team overseeing some of the testing. It was launched in March of this year, and it was deployed in April from NanoRacks from the International Space Station, and that shows it connected with BurstCube. And now we see both of them separated. So this was some good video that we got when it was deployed. Okay. We looked at some of the early data from SNOOPI, and I should say we had about 6 months in orbit with SNOOPI, and then the reaction wheels failed, and it re-entered about a month ago. But we were able to get a few data collections. This shows, one example here where it was in the low frequency range, the 250 to 270 megahertz, and this measurement was over the just off South America. And we see we do get these channels where we expected to see them from our knowledge of that communication signal. And when we look at the autocorrelation here, and then the autocorrelation at the specular delay at 5 of the communication channels within that band, and we see that we do see Our reflected signal, we see a good alignment between the different bands, and we're still working to process this data. That showed this for the first time at IGARS. Okay, so instruments and missions are important, but we need the algorithms to support the measurements that are going to come from these instruments and missions. So I'm going to talk a little bit about algorithm development. Most of this work was supported under a FINEST grant to my student, Seo Kim, who's now former student, Seo Kim, who's now at JPL. And we looked at developing a multi-frequency, multi-polarization algorithm based upon the SCOBY model. And so we looked at these 4 frequencies that we have been interested in that are available globally. And we looked at simulating a retrieval at those frequencies. So a couple things we looked at is, first of all, these are from different sources. So they're going to have different geometries. And how we handle that is we assume that the coverage when we make a given measurement is a random variable, and we looked at the statistical distribution of the incidence angles for the three different sources. These 2 frequencies are transmitted from the same satellite, and then we just picked from that distribution a combination of incidence angles in a large ensemble of simulations. Okay, so our retrieval is based on the simulated annealing. The distribution of water in the soil follow this principle of maximum entropy, or POMI. So it's not a physically based distribution. My current work is looking at a hydrological model for that distribution. And we tuned a model for the vegetation, the B parameter from SMAP data. And we used a model for the soil moisture. In the simulated case was actual measurements from soil moisture reference sites. So this was sort of an observation simulation experiment. We took a time history of 5 years of data from the SMAP CalVal sites, put that into SCOBY, generated synthetic reflectivities, and then inverted that to try to estimate the soil moisture and look at an error analysis of that retrieval. Okay, so we looked at varying 3 different things: the combination of frequencies and polarizations, the reflectivity error, so the error in our measurement, and the time window between when the measurements from different satellites are made, because they're not simultaneous. And so expected, as we increase the number of frequency combinations, our error decreases, no surprise there. We also found approximately a linear behavior between the error in reflectivity and the retrieved soil moisture. Again, no surprise there. And we also found a linear relationship between the time window and the error. And we actually showed that, having large time delays between the measurements really didn't have a huge impact on the error. So we could, look at, say, if we had a 3-day revisit time, we don't need to schedule the collections within that 3 days. We can just bin the data within 3-day blocks, and then we'll get reasonable results. Okay, we're trying to validate this experimentally. This is a tower I have just recently lowered after collecting a season's worth of data in a cornfield near Purdue University, and we have these commercial I-band antennas at 137 megahertz and GNSS, the S-band and antenna we believe quit working sometime during this experiment. We're still looking into this. One of my students designed the front end. Again, this is our first this and the EIRP monitor is our first real foray into microwave design at any level of sophistication. So we had a number of iterations on that, but we think we're getting good data from it. We collected data at this cornfield called the Agronomy Center for Research and Education, or ACRE. And this just shows the specular, the Fresnel zones for the different satellites we use. We are planning to this spring move to a forested area, the Martel Forest, which is also operated by Purdue. Okay, I'll say a little bit about the other frequencies we're looking at. We haven't done much in this recently. We did unsuccessfully write a proposal on this, but I think it's still an important area to look at. We're still pursuing it. And that is to go the opposite and go from very high frequencies that are used for wideband communication. So the thing we're using now is the wideband communication signal. So we look at altimetry, and we have this simulation where we have some eddy development off the coast of California, off the Monterey Bay. over 9 days. And we see this, the structure in the eddies. Then we simulated the SWAT coverage over those same days, and we see we have partial coverage of this eddy. So then we simulated a 8-satellite constellation using geostationary communication satellites in KU and KA band. We see we got pretty much complete coverage. I mean, it's sparse. It's not a swath like SWAT gives, but we still get more consistent coverage. Okay, so what do we need in order to do altimetry? And I know, early on from the very beginning, GNSS-R was, there was a interest using GNSS-R for altimetry, but there's a fundamental limit in that the available bandwidth is very small. And bandwidth is important because that has a direct relationship with the precision in measuring a delay or the sea surface height. So this just shows we applied on a log scale, so it becomes linear. Once I get above a certain SNR threshold, my resolution, my precision of my measuring of my delay, precision of sea surface height, depends very strongly on the bandwidth. So if I look at GPS CA code, about maybe 1 megahertz bandwidth, I'm going to get like a kilometer precision. If I go to the wider band GNSS, I'm going to get, maybe getting down to, I think I said this wrong. This should be centimeters. I'm sorry. So I get about a few meters precision. Then here we're going to get down to, maybe a few tens of centimeters, down to E5, which is a wider band GNSS signal. So in order to get down to scientifically useful altimetry, we need to go to things that are a few hundred megahertz of bandwidth. So direct broadcast satellites are typically within that range, and we get down into this 2 to 5 centimeter threshold. Okay, so we did an experiment. To see if we could demonstrate this with actual data. These are some repurposed DirecTV antennas. We got like a whole bunch of them on eBay when we did this experiment. And so we recorded the signal. We used a beacon as a way of calibrating the front end, so everything's phase coherent. This shows the recording system we used, and then we were able to show, in comparison with the LiDAR, that we got a pretty good unbiased estimator of the sea surface height, and that we stayed within the theoretical limits of the Kramer-Rao lower bound on the delay uncertainty, except for this one case. And we believe at this one case that we had overlapping footprints from the satellite, and so there may have been some thing was not, we couldn't really do the correlation properly with those. Okay, so now some conclusions. Where we are, I think signals of opportunity provides an opportunity for microwave sensing in bands that have previously not been used because of spectrum allocations. In order to get a subsurface soil moisture profile with vegetation, we looked at combinations of multiple frequencies and polarization. So that's going to be a requirement going into any mission or instrument design. SNOOPI will hopefully demonstrate the fundamental feasibility. We're still looking at the data from SNOOPI, but as a technology demonstration, we think we'll get some valuable information from that experiment to guide the future development of a mission. And we have an experiment going on in agricultural fields, which just ended, and going into a forest to validate the multi-frequency dual polarization measurement. And then in parallel, the wideband communications can provide hundreds of megahertz up to gigahertz of bandwidth for free for altimetry with much better global coverage and sampling. Okay, so in conclusion, there's a lot of signals out there that we haven't looked at with these basic ideas. What new things can we do with them? And of course, I have to acknowledge all the funding sources that were represented here. So thank you very much.
Great. Thank you so much, Professor Garrison, for your presentation. Can you hear me?
Okay.
So can you hear me, Professor Garrison?
All right, I'm watching the chat now. Okay, lessons learned from SNOOPI. Let's say we're still analyzing the SNOOPI data. Okay, we're still analyzing the SNOOPI data. So, in terms of the science, the instrument science deliverable from SNOOPI was still looking at that. In terms of the mission design and planning and all of that, I'll say, a few things. One, the parts of the mission, like the satellite bus and the integration and a lot of that, which would not really be the research part of it. I think I'll give the advice that if someone's planning one of these technology demonstrations, technology demonstration missions in the future, you'll really carefully plan that part of it and make sure you have sufficient testing and a good process for systems engineering in place, because many of the delays that we encounter with SNOOPI were kind of the spacecraft bus and those types of things, not really the on the science or the instrument itself. Okay, I'm sorry, I can't hear, Sean, I can't hear you. I don't know if
Yeah,
I got my audio turned up.
yeah, I'm not sure why you
Um,
can't hear me either, but it's okay. I've been entering the questions into the chat.
okay, switch to the other speakers. Can you hear me now?
I've been able to hear you. Can you
Oh,
hear me now?
that's what I meant to say. Yeah, I can hear you.
Oh, great.
Okay, I'm sorry. Yeah, sorry. I had you, I guess the speakers associated with this other monitor are not properly connected. So I switched back to
No
these.
worries. No worries at all. So I
Okay.
entered another question from the Q&A box
Okay.
if you want to answer. Yep.
Okay, fair. And I got this question, yeah, before the Faraday effect. Yeah, we're using these low frequencies, so there's going to be a big ionospheric effect. We do account for the delay of the ionosphere. And part of the mission planning, I saw that software that I showed uses the NEQUIC model. That's the basic ionospheric model that's used for Galileo. It's not, it's precise enough for everyday positioning. Just like there's a very simple ionosphere model that's used in GPS. There's a more sophisticated one, NEQUIC, that's using Galileo. It's still empirical. It's still based on climatological data. And so we use that to just align the delay window. So as long as our error is reduced so that we fall within the delay window, it met the requirements. And then for using it for science measurement, we use dual frequencies for these two sources, if we need to separate out the ionospheric effect, or we can, in post-processing data, go to a more sophisticated ionospheric model, like I think like GIM, some assimilated ionosphere model. Okay, Faraday effect. Okay, Faraday effect would be assuming the Faraday rotation and the polarization. So we are using circularly polarized antennas, for one. Second of all, we are making single polarization measurements in circular poles. So in the SNOOPI experiment, I don't know how much data we're going to get from the polarization of the signal. So we maybe need to go back in our analyzing the signal and looking at one of these ionospheric models, somehow, estimate what the Faraday effect is, or I don't know if that's going to be necessary for SNOOPI. Now, looking ahead for a science mission, the place I think the Faraday rotation may be important is again, looking at the polarization. So we would probably need to have dual pole measurements and also incorporate an ionospheric correction as part of the data processing and retrieval algorithms. But the big effect we take out from a model. Okay. Vegetation impact. Yeah. Okay. So we have this model, SCOBY, and we still are assuming that the scattering is nearly specular, and the scattering is coming from the vegetation soil surface. So the biggest effect of the vegetation would be the attenuation in the layer of vegetation to the soil. and again, that's one of the things we're trying to validate with these models. And it does
Great.
change the polarization too. So that's also, I think, one of the reasons why we need a polarization measurement too.
Yeah,
Okay.
great. Yeah, I think time for one last quick question.
Okay.
Was the expected depth of the subsurface soil moisture observations?
Yeah, if you go back to that one plot, and again, this is not that sophisticated of a model. I mean, it's basically just the Fresnel coefficient with one of the soil moisture dielectric models. I think it's actually the older Dobson model. And it looked at something like 20 to 30 centimeters in the definition of penetration depth. That's at the like the 350, no, 370 to 380 megahertz band. So going down to 137, we might get a little bit deeper, but it's something on the order of 20 to 30 centimeters.
Great. Well, thank you again, Professor Garrison, so much for your time, for answering all the questions. Thank you, everyone in the audience, for your questions and for watching today. That's it for today. If you want to contact Professor Garrison, you can go to his Purdue University webpage. So thank you all.
All right, thank you very much.